Dear friends, welcome to one more video lecture in which we are going to study the differential equation of linear simple harmonic motion and how to obtain the differential equation of linear simple harmonic motion. For that, again we will start with the spring mass oscillator. Here I got a spring. The free end of the spring is attached with some mass. The spring gets elongated. As soon as you remove the mass, the spring will come back to its original length because of the property that is called as elasticity of the spring. Let us consider the mass is attached to the spiral spring, and on the board I will mark the position of the spiral spring when it is suspended from a fixed point. Let, with the mass attached to the spiral spring, the mass rests at some position which is represented by the equilibrium. Now, let this mass is pulled so that it will be displaced to, I will mark here the extreme position up to which I have to displace this spiral spring. This is the position up to which I have to displace it. This is the positive extreme position to which the spring is displaced. Then, if it is released, what you will see that the spring will oscillate between these two extremes. This is one extreme and this will be the other extreme, and the oscillation will be damped. It will come to end after some time. This is about how the spiral spring oscillates. What is the physics behind it? When it is pulled down, a restoring force is developed in the spiral spring which make it to move up. While moving up, its velocity at the mean position becomes maximum. It will continue its motion to the other extreme, and again a restoring force tries to bring back it to equilibrium. Like this, the motion is between the two extremes along the straight line. It repeats again and again on the same line, therefore it is periodic motion. And in this motion, as we proved earlier, the force or acceleration is directly proportional to displacement, and force and displacement are opposite to each other. Therefore, as we stated earlier, linear simple harmonic motion is defined as, it is linear periodic motion in which force is directly proportional to displacement. Force and displacement are opposite. All the three things are written in one equation, that is, F is directly proportional to mass of x. With this I will write this force is equal to mass of k into x, where k is a force constant, and this force constant is equal to the force per unit displacement. Now actually what we know is that according to Newton's second law of motion, the force is equal to mass into acceleration, and hence the same equation, which is F is equal to minus kx, can be written as mass into acceleration is equal to minus of kx. This is the equation of linear simple harmonic motion. But here x is the displacement, and if x is displacement, then the velocity v is equal to dx by dt. Here, dear friends, what you have to remember here is that the motion is periodic. There is continuous change in the position of an object. Object moves from mean to extreme and extreme to mean again and again. Therefore, this displacement we are thinking of is the displacement at a given instant of time, that is instantaneous displacement, and that to be measured from reference point, that is equilibrium. If x is the displacement at a given instant of time, then dx by dt is the velocity at a given instant of time. Therefore, this velocity is the instantaneous velocity. This instantaneous velocity is dx by dt. If dx by dt is the instantaneous velocity, then acceleration, which is also instantaneous, is dv by dt. Rate of change of velocity is the acceleration, and therefore it should be equal to d by dt of dx by dt, because velocity is dx by dt. Therefore, I will write acceleration equal to d2x divided by dt square. Acceleration is the double derivative of displacement. It is second derivative of the displacement. And using this in the equation of the simple harmonic motion, I will write it as m into d2x by dt square is equal to minus of k into x. And using this equation, again I will come to the equation that, rearranging the terms, I will write this as m into d2x by dt square plus kx is equal to 0. By bringing minus kx to this side, you will get the equation d2x by dt square plus k divided by m into x equal to 0. Here k is the force constant. What k is? K is the force per unit displacement. If k is force per unit displacement, k by m is acceleration per unit displacement. Therefore, k by m is a constant which is called as acceleration per unit displacement, and hence you will have d2x by dt square plus omega square into x equal to 0. This is the second order differential equation of linear simple harmonic motion. This is how to obtain the second order differential equation of linear simple harmonic motion. It is started with the definition of linear simple harmonic motion. What is that? Linear simple harmonic motion is linear periodic motion in which force is directly proportional to displacement. Not only force or the acceleration, because force and acceleration both are in the same direction. When I am saying that F is equal to minus of kx, mass into acceleration is equal to minus of kx, acceleration is equal to minus of k by m into x. This means that acceleration is directly proportional to minus x. Therefore, linear simple harmonic motion is the linear periodic in which force or acceleration is always directed towards a fixed point, and that fixed point is the equilibrium, and the magnitude of force or acceleration is directly proportional to displacement measured from the equilibrium position. With this definition, we started with equation of linear simple harmonic motion as F is equal to minus kx, where k is force constant. Actually, force constant is force per unit displacement. This k is force per unit displacement. Then k by m, we will treat it as omega square, and this omega square is force upon mass acceleration per unit displacement. This is one more thing that we get in this video lecture, that omega square is nothing but its acceleration per unit displacement. This omega is a constant term for given linear simple harmonic motion. It plays very important role in finding out the frequency of oscillation or the period of oscillation in simple harmonic motion. This is how to find out the differential equation of linear simple harmonic motion. I hope you might have been followed this one. You are able to understand the concept, and hereafter we will see how to derive the different physical quantities in linear simple harmonic motion. That we will do in the next video lecture. Till then, bye, be safe and stay at home. Hereafter, I am giving you the link of previous video lecture in the description box. Therefore, it's my request to all of you to subscribe my channel and go through the video lectures so that you are able to understand the concept of physics clearly and you are able to achieve the expected results in the coming examinations. Thank you very much.